Okay, so before we move on to viscous around flow around flat plates with turbulence, I want to talk about turbulence in general. We've kind of saddled up next to it a couple times throughout the semester, but I think it's time to actually sit down and talk in detail about what turbulence looks like and what effects it has. And this is because it plays a huge role in our lives. I've said many times over the semester that we live at relatively high Reynolds numbers. Car drives in turbulent flow. Planes obviously fly in turbulent flow. There's evidence that turbulent flow or separated flow with turbulent flow in your bloodstream can cause problems in your arteries. If you have a poorly designed split in your arteries, it can cause huge problems. Designed, you know what I mean? So it's a huge thing, and in more, I guess, practical and mundane kind of ways, it's important. It's tremendously important for heat exchangers and all kinds of those kinds of things, right? Mixing in chemical reactions, it's tremendously important. And for a long time, it was one of the great problems of science. So we understood how bulk fluid flow behaved. It's something called potential flow describes it really quite well. With potential flow, we say, well, we know how the derivative of the velocity has to behave, and then we back out what the actual velocity is that satisfies that differential equation. And it worked really well for describing flow around an object. But it failed in pretty spectacular and important ways. For example, the drag on a ball is calculated using these methods was much lower than actual measured drag on the ball. And in particular, something that happens, it's called a drag crisis, which causes the drag on a ball to drop at a certain Reynolds number. And that was just baffling. They couldn't figure out why it happened. And around this time, they started working on the physics of boundary layers, and they were able to talk about laminar viscous boundary layers, and they were able to understand those, but combining this external flow and this viscous layer next to the object was incredibly difficult, mostly because the viscous layer next to the object is so small, and it has a really outsized role on the behavior of the whole system. So how to combine those two and connect them mathematically and through models was tremendously difficult, and still is. It still is tremendously difficult. And just as a reminder, with laminar flow, we have nice, even, symmetric, let's draw the stagnated one out here, streamlines that come around an object like this. Oops, didn't draw that very well. But with turbulent flow, we have interesting things that happen when you come flow around an object. If we're looking at a sphere, the front of it looks actually quite similar to laminar flow. And then at some point, it stops and separates back, and we have this large recirculation region behind the sphere. We've talked about this. It's a low pressure region. It causes much of the drag. And understanding when, how, and why we get flow separation at this point on a sphere is very important, and also understanding why this moves with Reynolds number, because as you increase the Reynolds number, this moves down towards the back, and that is a result of turbulence. Turbulence makes that happen. We'll talk about that for certain. So first, some notation about turbulence. if we look at the, with laminar flow, if we were to look at the velocity with time, we would see it would be a constant line if we plotted it on this plot right here. It'd be just a straight horizontal line, just like this dashed line here. Turbulent flow, though, is random, utterly random. It has fluctuations around this line, and this average velocity, the line it fluctuates around, is called u bar, lowercase u bar. And remember, lowercase u is the x component of the velocity. But right now, we're just going to focus on the x component of the velocity. But you can treat all of the components of the velocity the same way, v and w. And any fluctuations away from the average here, let's do that in red. I think it's a little bit more visible. Any fluctuations away from the average are called u prime. U prime. So we can the velocity at any moment then, u is equal to u bar, the average velocity, plus the fluctuations away from the mean. Okay, once we've described it this way, we can start talking about the magnitude of these fluctuations and what they mean. So we can kind of take the squared average, right, which is 1 over the time of the integrated t naught to t naught plus, let's call this delta t, plus delta t of u prime squared dt. So we can integrate the velocity over time, squaring the deviations. So this is like the root mean, sort of like the root mean squared, right? But we're not taking the root. It's just the mean squared deviations of the velocity. And that turns out to be really useful because we can non-dimensionalize it, as fluid mechanics people like to do. And we can divide the square root of the fluctuations by the average velocity. And the result is a description of turbulence magnitude. And it kind of makes sense, right? We have the root mean squared deviations divided by the average velocity, so we're normalizing it by the strength of the average velocity. And it turns out that in our lives, by the way, this is a capital cursive I. I don't know how many people know that. I don't even remember if I remember how to write it now. Yeah, there we go. So capital I is equal to 0.01, and that's good. If we can reduce the turbulence in our flow, like in a wind tunnel, to 1% of the mean flow, that's actually quite good. If we can reduce it to 0.0002, that's world-class wind tunnel. That requires a lot of care in how you do everything associated with the wind tunnel. A lot of care. We can also say that I is equal to 0.1, and that is roughly where we live. So as you move around in your day, the turbulent flow is usually about 10% of the mean flow that you experience. So this random fluctuations in velocity, which by the way are in 3 dimensions. So, remember when we had we had flow between 2 plates where one of the plates was moving, there was some velocity v, and we said, oh, it's beautiful because we get this gorgeous linear velocity profile. If we increase this velocity v beyond a certain point, the flow inside of here ceases to become laminar and it becomes turbulent, in which case we get flow mixing down and up, but also into and out of the page, right? The flow becomes fully 3-dimensionally random, even if we don't have driving forces in that other direction. So even though here we might say in our Reynolds, X, Y, Z, even though when we were solving Navier-Stokes in this case, we might neglect the z direction because there's nothing happening in that direction. Once we hit turbulent flow, once we've increased velocity v beyond a certain point, we will get random fluctuations in velocity in the z direction regardless. And so we cease to become a two-dimensional or one-dimensional flow, and it becomes fully three-dimensional. It's another reason turbulence is relatively difficult. So with shear stress, we get nice laminar flow, which is roughly parabolic, not quite, with the velocity gradually increasing away from the solid surface. Let's say we have a free stream velocity like this, where it's a constant u coming at the surface. And this is, like I said, roughly parabolic, and we know from our models that shear stress at that surface is equal to mu du dy. Again, let's define this as x, and this is y. Now, with turbulent flow, it's a little different beast. So the first of all, the shape of the flow is much different. You get a very shallow, high gradient in velocity. So very high velocity gradient near the bottom, and then it gradually increases for a while after that, but that's a very gradual increase. And the reason it's a very gradual increase, like we've mentioned before, is because inside of this flow we have a tremendous amount of mixing going on. Slow fluid is moving up, fast fluid is moving down. The magnitude of the mixing changes all the time. We have small amounts of mixing, we have large amounts of mixing, and it causes this region here to have a relatively homogeneous velocity. It forces this shear stress to occur, the velocity gradient to occur in a very narrow region. It also increases the shear stress experience, because not only do we have the normal shear stress experienced by two different layers of fluid that are moving at slightly different speeds, where the top one is dragging on the bottom one trying to move it faster, or you can think of it the opposite way, the slow one's trying to slow down the fast one. Here we have that occurring, but we also have this mixing occurring. We also have rotational flow, viscous dissipation due to these eddies and vortices that are occurring that dissipate the energy. And so this tau is no longer equal to mu d average velocity dy, right? You think it would be, but it's not. It's not equal to the gradient to the average velocity with respect to y. Instead, our turbulent flow shear stress is equal to mu, we'll extend that, du bar dy, let me rewrite that just so it's clear. That extra bar shouldn't be there. Dy minus rho u prime bar v prime bar. And so we're taking, remember, these are the average fluctuations, squared fluctuations of the velocity in the x now in the y direction. And we're multiplying it by the density, because this is a very inertial thing, right? These are inertial effects, not by the viscosity, but by the density. And we're taking these fluctuations and we're subtracting them from the shear stress. So this section here is called the Reynolds stress. Reynolds stress, and it's equal to the turbulent shear stress. And this is, by the way, just one model for the extra shear stress that occurs due to turbulence. It's a good one, though, but it's just one way of modeling that extra shear stress that occurs. Because of this tremendous amount of mixing, we end up taking this boundary layer and splitting it up into three parts. There's a fully turbulent layer, and this fully turbulent layer has all the mixing we would expect. And I'm drawing these arrows this big on purpose. As we get closer to the ground, these arrows start to be blocked, if you think about it. This arrow, for example, here is too big to actually go reverse its direction and go down. So we get smaller amounts of mixing simply because we're geometrically constrained by the wall. And this is called a transition region. And then we have a viscous sublayer very close to the wall, where because our velocity gradient is so high here, in this region, our shear stress is huge and it dominates our flow. And so even though we have a lot of inertial effects going on above it, here our viscous effects are so high that we have viscous dominated flow in this small region here. It also helps that the turbulent flow mixing is dampened by the presence of the wall, right? You can't mix very well if you're stuck up against a wall, if you think about it, right? Yeah. So there are ways of estimating the velocity profile, which we're not, obviously I'm going to test you guys on this, but I just want you to know that they exist. And when we're trying to estimate the velocity profile, really what we're trying to estimate are non-dimensional velocities and ratios of average velocity to things like shear stress that we can measure. So we can say that the average shear stress divided by U star is equal to y times U star divided by nu, where U star is equal to tau W, tau at the wall, divided by rho to the 1/2. There's an overlap region, that transition region, where our velocity profile then is equal to U bar over U star, which is equal to 2.44 times the natural log of y U star divided by nu plus 5.0. Again, where U star is equal to this, so we just plug that into there. And we have an outer region. By the way, this is fitted experimentally. In the viscous sublayer, right, everything behaves nicely, so we can actually plot this. We can analytically determine the profile. Then the outer layer, actually it can vary quite a bit. So what we say is U bar divided by U star is equal to 1 minus R over big R times 1 over N, where N is used to fit our velocity profile as well as we can. This is called a power law profile. Power law profile. And the end result is we get, as N increases, we get increasingly steep velocity profiles that look like that. And a lot of things affect what power law works well, right? The nature of the turbulence, how strong the mixing is, what kind of mixing is introduced, what's causing the turbulence. Is it roughness? Is it vibrations? Is it just the speed of the flow? How long has the turbulence existed? Because turbulence decays, you get these large eddies that break up into smaller eddies, which break up into smaller ones, and it decays, and eventually the small little fluctuations dissipate due to heat, dissipate into heat, right? All that kinetic energy. So it's really quite a complicated situation, and there are lots of people studying it. Yeah, so that's turbulent flow. Next one, we're going to talk about specifically turbulent flow with boundary layers.